Okay. After my little ramble there, let's invite the next speaker. So Pierre Belmoral, also from INRIA, same institution as Emma. Pierre, reveal yourself. There you are. Hello, Pierre. It's been a few years since we last saw each other.
Sorry for my cat. He's still sleeping all the time.
Don't worry. I don't know if you noticed, my dog crawls all over me. Every time there's something out the window, she wants to see this.
Okay, so I start?
Yeah, go for it.
Okay, so partager écran. Let's see, it's done. Done. No, fenêtre. So first of all, I would like to thank Emma for her very nice talk on these branching particle methods and the neutron transport equation. Another thing I would like to say is to thank Andreas and Alex for their introduction to the physics of nuclear plant model. I just hope that all of these systems will be stable to some, let's say, normalization control. That's one hope. So my talk will be more modest, I would say. I will just talk about simulation. So in this talk, for example, the particle methods will be interpreted as samples. So there is no physical meaning on these particles, except that they are used to sample something. So let's start with the talk. So here is the talk I will discuss on, let's say, an introduction to Feynman-Cake particle interpretation. And I will give you a way to do a particle Gibbs associated to these models. So something I would like to say that it's the pioneering article on this subject was done in 2010 by Andrieux Doucet-Hollenstein. They had a huge impact in statistics, I don't know in physics. And in fact, I spent 4 years to understand why it was working, because it's always a system of notation, and my system notation may not be the best one, but to translate one side to another was difficult to me. So that's why we did some work in 2014 with Robert and Frédéric. But the talk of today will not be in discrete time, will be only in continuous time. So I put the links, so you just click and you will have the articles. So if you want another introduction on particle methods to approximate Feynman-Cake models, you can look at the paper we did with Miklo and let's say 20 years ago. And Matthias Rousset also did a lot of work on this subject. So I didn't describe all of them. And I particularly enjoyed the last one on the stability of these equations. He did with Ferré and Gabriel. So here is the two ideas I would like to show you. One is how to approximate using particle of Feynman-Cake equation. And second, how to do the particle Gibbs associated to these models. And of course, the impact on branching will be not so large because this Feynman-Cake measure represents the intensity of the branching process. So it only corresponds, as Emma has shown, the first moment of a branching process. So there may be plenty, it doesn't represent the branching process itself, but it tries, the particle methods I will present you, tries to mimic the branching process with a finite number of samples. So let's start with this. So first, some notation which are quite standard for everyone. The first one is the integral. I will denote like that. It's like if you have a row vector and a column vector, so it's a matrix notation. The same for if you have an operator, I will write the transport on the action on the left, action on functions, like that. Iterates of transitions, I will use this notation, but I think everyone is know all of this, but don't be surprised because I will use them quite often, at least at the very end. So this is an integral, this is a transport, and this is the action on function and iterations. And instead of writing complicated formula like that with the total variation, some constant that may not depend on the time and epsilon, I will write that mu epsilon, it's almost mu plus minus something, okay? So this notation means something like that. Okay, so let's go, let's enter into the models. So I will consider a Markov process evolving in some metric space and some potential function. I will assume here positive. And I will consider always the historical process, we write it like that. So x hat, with a, if you have a Markov process, if I put a hat, it means all the historical process from 0 to t, and it belongs to the space of trajectories.
Pierre, may I just stop you for a moment? Your slides seem to be very squished at the moment. I don't know. Is there a ooh.
It's better.
That's better. Yeah, if you could just kind of expand it to the full screen, that probably will work better. It might be a Mac thing. I use Macs and sometimes they do.
So if I do agrandir like that, no, it's the same. What I did is this, and it doesn't work.
Yeah, no, that was the one that was squishing it. Okay, well, let's work with this.
Let's do like that, and I
exactly. Yeah, no,
okay.
you can.
It's better.
Yeah, that's fine. It's perfect. Thanks.
Okay, so if I put a hat on some Markov process, it means the full history, and it lives in the past spaces. And if I have a potential function acting only on the terminal point, I can extend it on this historical process like that. Okay, so I will consider only if I have a potential that depends only on the terminal state, I can define v hat. I extend v hat on the path, only like that, okay? So let's continue. So now it's becoming complicated. Okay, so in discrete time is quite standard, because if you have a Markov chain, you consider the sequences from 0 up to time n. So of course you live in product spaces, and there is an obvious stochastic calculus. But if the formula are relatively stable with respect to this notation, when you talk about the Markov chain on some state space, you can consider this as a Markov chain on some state space. So if the formula doesn't require some regularity on the process or on the state, you can consider the past space version, and you will see that in terms of particle, this allows you to consider the genealogy. When you do a branching, you branch a trajectory. And of course, they evolve separately, because if you branch, you will have two trajectories and so on. So that's one trick. And in continuous time, so it's a little more tricky, because you need to work with the infinitesimal generator on cylindrical functions, so we did that with Laurent a few years ago, but there is a new viewpoint, I think, which is very interesting, is the one developed by Dupire, Ramacon, Fournier, and in the PhD of Saporito. It's based on an Ito functional calculus that extend, let's say, the test functions. Instead of considering cylindrical test function, you can consider other type of functions like integrals or supremum or anything like that. So in any case, this is just to say that if I have a Markov process, I can consider also the historical process, and I put a hat just to fix the notation. And if V is only depending on the last, I extend on the historical process in that way. Okay, so that should be quite clear. So here are my Feynman-Clark measures. I consider the law of the historical process. So PT is the law of the historical process. I consider a potential function, which as I assume here is positive. Yeah, I may extend it as depending on the history. And Z is a normalizing constant. So this is quite simple. So it's simply the weighted measure of the historical process by some exponential factor. That's it. Okay, so the first, if you prefer the weak formulation, it means that the measure acting on some function on path space is the expectation up to some constant. That's a weak formulation. And okay, that's not so easy now. Yes, so if you consider the time marginal, it's here, you take a function that depends only on the terminal time. And of course, you will have the function that depends on the terminal time. And you will have, because the potential depends on the terminal time, you end up with this formula. So you see this formula and this formula, if you don't specify the state of xt, looks very similar. And in fact, it's true, because if xt itself is the historical process of another process, then you come back again to this. And in fact, even more complicated, because you will have a potential function, more depending stuff. But the idea is to say, if I write this or I write this, is exactly the same, except that I consider historical processes. Okay, that's it. So that's the idea. Is to, if I look at the time marginals or the past space measure, if you don't specify and you work with an abstract Markov process and a potential that depends only on the terminal time, so if you work with this, it encapsulates this type of models, if you don't specify some regularity property. The same, another observation is that because you have an expectation like that, for a given Feynman-Cach measure, there are many ways of writing this Feynman-Cach. For example, you can change x by an exponential change of probability, and then you change the potential. Or you can change the potential and change the drift of x. So there are many ways to write a given measure like that. So if you decide to write it with the x like that, it means that I will use this as the exploration of the space. If I have the v, it means that I will kill with this one. But of course, if you change the v and change the x, it will be another algorithm, but mathematically it's the same. Okay. Okay, so the particle sampler of these Feynman-Cach models are very simple. In fact, I'm working on path space. So I have capital N path particles. Each particle is a trajectory. S represents the ancestor at time S. I is the index of the particle. It is defined in this way. Well, you start IID as X naught. And if you have X naught is distributed according to some law, you start with IID samples from this law.
Yeah, if you reduce the scale, so you fit one slide in the page, then you can just tap up and down as you would expect normally.
If I reduce it, I go straight to the full.
No. In the top left, it says échelle. On réduit l'échelle un peu.
Réduit l'échelle. Où ça? Where?
No. On the actual window. It's your previous, next, avancé.
Okay. Yeah.
So reduce it to a single page per screen.
I think it comes from this. Oh, okay, it's fine.
And now you can just advance a page at a time.
It's not so.
Yeah, it looks good. Yeah, it looks good.
Okay, so you start IID, then you between the jumps because there will be jumps. You do the same exploration as the historical process. So it means that each path is extended as the historical process will do it, is extended to the next jump. Okay, so you have the path and you extend the path until the next jump. When the jump appears, so you do that at rate v hat. When the jump appears, it's quite simple. You kill the particle and you jump uniformly inside the pool. So cannot be simpler than this. You extend the trajectory, you compute its lifetime. If its lifetime, so the integral of the potential on this is above some exponential, you kill it. And then you need to have the same number of particles. So you choose one of them in the pool. Okay, so that's quite simple. The historical process, of course, is not the same because here, the historical process is all the particles you have sampled from 0 up to time t. Each of them is an ancestral line. Okay? So there are two things here, not to mix. The historical process of all the particles you have sampled. And if you pick one of them at a given time, you will have the ancestral line from 0 to time s. Two pace models. Okay. And then there is another object that we consider is the empirical measure of the terminal time particles, which represent each of them a genealogy, the ancestral line of the ith particles. So psi it is an ancestral line. And here I consider the empirical measure on the ancestral line. Okay, so I repeat, you have path particles, you start IID, you extend each of them, so you keep track of all of them, you extend each of them. When one is killed, you kill all the trajectory, duplicate the trajectory uniformly in the pool, and continue evolving. Okay? And at every time, you have a genealogical tree, and if you pick one of them at a given time, you have all the ancestral lines. Okay, so it's a little abstract, but you need to keep in mind that we are working with trajectories which represent the ancestral lines. So that's the full history, and each of them is an ancestral line. So if I look at the very end, I have an ancestral tree, and I look at the occupation measure, and I pick one of them randomly. Okay, so these are the notations. I think I cannot simplify more. Psi t is the particle model. X double bar is I pick one ancestral line at the very end randomly. OK, so...
Pierre,
oui.
C'est Tony qui parle. Est-ce que je peux juste te poser une question? Can I just ask a question on the notation? So when you kill a guy, you kill it completely. So it means that you completely forget its trajectory, correct?
Yeah, but it's still here.
It's still here. You mean it's still here, but it is a copy of another one. Or
yeah, I mean, you run this. It means that you run the particle model from 0 to t.
Mm-hmm.
And of course, when you run it, there are some guys which have disappeared, blah, blah, and so on. At the very end, at time t,
yes,
you have n ancestral lines from t to 0.
Yeah, yes, okay.
But here, because you keep everyone from 0 to t, at each time, you have a genealogical tree.
Yeah, okay, thanks.
It's difficult to have the two in mind because this may represent the genealogical tree, which is not the case. So this is where it can be complicated. Okay, so
sorry, Pierre, can I just ask, because I'm just a little bit confused. So the particle jump to the position of a new particle, or it's whole path which adopt the path of the other particle?
When you work in path space, it's by definition, the space is the path, is the path.
Yeah.
So you kill a path and duplicate a path.
Okay.
And when you jump into the path pool, it means that you are killing one path and you are jumping into one path. So it means that now you will have two passes in this location.
Okay.
And then between the jumps, you extend the path. If you have two paths, you extend two paths differently, of course.
Okay.
As the historical process will do.
Okay. So it's like a growing tree, but it always has end leaves, right?
Yes. And this is when you look at the very last time, you have only one tree. But if you look at every time, you have all of them is a tree.
Mm-hmm. Okay, thanks.
So of course, you cannot do it in continuous time like that. So you need to discretize something. So if you discretize, it will show you some connection. So you take a time scale like that. You start IID again. Between the jumps, you do the exploration of the process step by step. For example, an Euler scheme or something else. And now you replace the killing and the jump by sampling n times according to this. So here, you look at the particle psi I. With this probability, you say no jump. Delta t is the time step. So if delta t is 0, small, very small, most of the time there is no jump. But with a small probability, which represent more or less the chance to jump in the DT step. When the jump occurs, it means that you kill the particle and you replace it by choosing one of them uniformly, one of them according to its weighted measure. Okay? For each particle, you do this operation. So with this probability, you stay. With this probability, you are killed and replaced by a new guy chosen with this probability. Of course, when delta t tends to 0, most of the time you have no jumps, and these geometric jumps becomes an exponential jump rate. And when delta t is close to 0, this is close to 1/n because it's 1, 1. So this shows you the uniform choice in the pool when delta t tends to 0.
Okay. Pierre, can I interrupt again? Sorry, it's Julien again. So it is important that you use the potential both to decide the rate of killing and the choice of the new particle.
Okay, if you eliminate this, you can eliminate everything I'm saying will be true if I put epsilon in front.
No, but I mean, is the weighting is done with the same function you use for the
yes, of course. Yeah. You need to take, this is the only way to represent an exponential jump for the killing and a replacement by uniform. You can replace this by uniform.
Okay, sure, of course, thanks.
But there are some people that prefer not to do this acceptance and look at the full selection. It means that at every time you decide to reconfigure all the guys by sampling n guys according to that. But this doesn't really like the limit when you take delta. Sorry, it's delta here, it's not delta.
Okay, of course, sorry. Thanks.
Okay, so this, you can see this as a genetic algorithm because you are forgetting this, you are selecting endpoints. Well, the ones which have been rejected, you have selected endpoints according to better fitted individuals because you were killed, very likely, and you have chosen to replace your location by a new location randomly chosen according to that. So this is typically, you have a selection of the population, you reconfigure. You reconfigure the population, you can say as you want. So if you want to see what we wrote some ideas in a paper with Jacob, Murray, and so on this subject. And maybe there are plenty of variants. Here I have considered V is negative. V is positive. So I only consider this case, but there are plenty of variants where V can be positive or a positive part and a negative part. There are many ways of writing things, but at the end of the day, it's always like that. You kill and duplicate some guy according to some well-chosen distribution. When V is, when you are considering only this case, in this situation, you are killing and uniform choice in the pool. So in fact, this is what I just add this based on based on the previous talk by Emma. In fact, the Feynman-Cag model, it represents the intensity. So the first moment, it's unbiased. Okay, so we can show that the first moment is unbiased. So you take the branching process, look at the occupation measure, look at the first moment, so the mean of the sum applied to some function, and up to the number of particles in the beginning, you end up with the Feynman-Cag model. The Feynman-Cag model, I gave you a particle algorithm here, and this particle algorithm tried to mimic with a finite number of samples, which is constant, the evolution of the branching process up with an unbiased in some way, but it tried to mimic this, okay? So here, because V is positive, I have minus V. It's pure, I'm killing particles all the time. So if you kill someone and you want the size fixed, you need to duplicate in some place. Okay, but so just a link with the branching process. Just to give you some equivalent names. So there are plenty of names. The genetic algorithm is the most as you can see, is a natural name. Is related to spatial branching processes for the reason I'm just talking. Just the Feynman-Cag model is the first moment of the branching process. There are plenty of things, but I have no time because of all the questions. Diffusion Monte Carlo also. So these ideas, in fact, the algorithm I'm just describing is not new at all. I have not invented anything. It's more or less inside all of these works, especially the one by Etherington in discrete time and Rosenblut for molecular chemistry. So it's like more in past space. These guys are really introduced this type of reconfiguration ideas. So this is something we did some years ago, is to put some rigorous mathematics inside this type of models. And if you are a little disturbed nowadays, there are plenty of names. So I put some names. When you do the selection, you can call that resampling because you reconfigure or you resample rejected particle. Enrichment. The one I like is the go with the winner. If someone is killed, of course, it's better to go with someone who is not killed, so you go with the winner. Quantum teleportation is a friend of mine working in physics who has done this, because when you kill someone and instantly another one duplicate, you need to explain physically what happens. So apparently it can be seen as quantum teleportation. So there are plenty of names. I think today you will have a talk on quasi-stationary Monte Carlo method. I don't really like quasi-stationary because in fact the fixed point is really a fixed point. It's really a stationary point. So there are plenty of names. If you have new names, it will be, you just tell me and I will update these things. Okay, so now let's enter in the mathematics. So the first thing to look is the central limit theorem. It tells you that if you take the occupation measure of the genealogical tree you have at the final time, you will end up with the Feynman-Cag model on past space plus 1 over square root of n, something which is almost the Gaussian fit. Okay? So that's the Monte Carlo approximation. This is just telling you that if you take the empirical measure, you subtract the limiting, you multiply by square root of n, and you end up in the limit by a Gaussian fit. Okay, so it's simply as simple as this. There is also a bias because it's not a perfect simulation algorithm. If you look at the law of one ancestral line, it will be the law of the Feynman-Cag model on past space, but when you have enough stability, then you will make an error in total variation of order t by n. So if you want to estimate trajectories, the law of the trajectory, you pay the length of the trajectory divided by n. And if you look at the law of the ancestor, there is something wrong here. It should be the marginal of this on the ancestor. I should have written QST. So it's the Feynman-Cag measure marginalized on the terminal time S. You will pay T minus S. Okay. So the idea is to say, if you want to estimate trajectories, the best you can expect is time by n. If you just look at the terminal time, of course, the terminal time will be uniform in time. So we can estimate in the best scenarios the marginal in time Feynman-Cag models without past spaces uniformly in time. Okay, so, and there is one important property, which is the one I will insist a little bit. If you look at the law of the ancestral line of the particle model, it's biased. But if you multiply by this extra factor, which is exponential minus the empirical measure and the potential. So you are taking the empirical potential values, you integrate them from 0 to t, you multiply the law of x, which is biased, by this term, and you have exactly the Feynman-Cag model. So this guy is biased, but if you multiply by this, you get something unbiased, which is a bit strange, but it's some property which can be proved using martingale and semi-group decomposition. If you multiply by this, it's unbiased. Okay, so now let's go to the next. So it's not so new. Yes, it comes from at least 30 years in discrete time. Okay, so now I come back to the unbiased property. I take the law of the ancestral line multiplied by this. I said it's unbiased. And I'm just defining new distribution, which is the same as this, but here I plug all the particle model from 0 to t, all of it. I put all the particles from 0 to t, and I create a new measure, which I call it, we call it many body Feynman-Cake measure. It's not my idea, but it's called like that. So you put all the particle model, you take one ancestral line at the end, and you create a new measure. And this new measure, the only thing I will use now is that it's unbiased. If I look at the marginal on this, it's unbiased, and it's exactly what I want. And here is all the particle model. So I will reduce a little bit. Yeah. So if you want to do a metropolis testing associated to that, it's quite simple. You sample one pair, you sample another pair, and you accept or reject with the ratio. And if you accept or reject with the ratio, each of them tends to the same quantity, then your acceptance ratio will tend to 1. So that's called independent particle metropolis testing in statistics. It's interesting, but the problem is that the ratio tends to 1, almost surely. The acceptance ratio will tend to 1, but there is a lot of fluctuations. Okay, so here we go. So now let's look at this and think this as a measure on 2 variables, all the particle system, one ancestral line. I define this as a probability measure, and I want to do a Gibbs sampler. So if I want to do Gibbs sampler, I need to sample the blue given the red. Sampling the blue given the red is very simple. If you give me the particle model, I look at the terminal time genealogical tree, and I pick one trajectory. So to do this operation, the blue given the red, is very simple. The question is how to sample the particle system if you give me one ancestral line. That's more complicated. How to sample the particle model given when you give me one ancestral line. But with respect to this law, I'm not talking about without this weighting factor. So here we are. I'm just telling you how to do this operation. So the idea is to fix, of course, if you give me one ancestral line and you ask me to sample the corresponding particle model, this has to be an ancestral line all the time. So the idea is to say, to define another particle model where every time the first particle, say the first, is always this ancestral line that you gave me. So here is the algorithm. So you sample IID as before, keeping the first, let's say, equal to the start of the ancestral line. Between the jumps, you do independent and the same as before. But now you modify the killing rate, just adding this factor. And you jump uniformly on the pool, so this is the same. But there is an extra jump rate on which you jump on the ancestral line. So it's not so simple to see, but it's more or less the same as before, except that there is a small jump rate at which you jump on the fixed ancestral line. And you have a softer killing of that form. So in that way, without the blue, if you put this out and put this equal to 1, it's exactly the same model as before. So the only difference is that if there is these two things, and we can show that this particle sampler coincide with the model I've defined before, but a Feynman-Cake model where you replace V by this quantity, and you replace the evolution you have here by this evolution plus an extra small jump rate on which you jump onto this one. Okay? So it's almost the same model as before, except that you have less chance to be killed, but you have a little chance to jump on the path you have fixed. Okay, so this is the terrain we obtained with Mark.
Oh, sorry, Pierre.
Yeah.
I got distracted just a minute, but so it's probably just me. But this X double bar XS is given to you. It's one of the...
So you give me one ancestral line, and this ancestral line is fixed. I don't want to touch it.
Okay.
Okay. And I do the Feynman-Cag model I had before.
Okay.
With one less particle. I kill the guys less often, but they have a little chance to jump onto this.
So it's a little bit like a source term or something?
It's a frozen term.
Okay, thanks.
So now we have this formula that tells you that the many body measure I have, all the particles, one ancestral line, we weight this term is the same as the model I've just defined. If you give me one ancestral line, I define this system as before. So here, this system is the one I've just defined here, where he has a law, he has less chance to be killed, blah, blah. If it's killed, it's uniformly in the pool. And in the pool, you have the line. Okay? In the pool, you have the line. Okay, so now, thanks to this, you can do exactly what I did, how to sample the system given the ancestral line with respect to this law, with this weighting factor. You just do exactly what I described previously. Okay. So the discrete time version, if you want to do it, is a little more complicated to read. We didn't find good notations. Maybe it can be improved. So the Gibbs sampler is simple. You start. T is not the time. Is not the time of the algorithm. T is the length of the trajectory I'm working with. So what I'm doing is, I take a trajectory of length n. I sample all the particle system with this frozen trajectory I've just described. And then I pick one of them, one trajectory uniformly. Okay, pick one trajectory, start with the trajectory, run the particle system with a frozen trajectory, and then pick one of them uniformly. Okay, so you obtain a transition in path space. You start with an ancestral line and you arrive to another ancestral line. And in the middle, you have sampled a particle model with a frozen ancestral line. So this is the Gibbs sampler. And the transition from here to here is very simple. It's the mean of a function of this, if I fix this. And this is a sample from the uniform. So you replace is equal to this. So in fact, to understand the evolution of this transition, the stability, of this transition, you simply need to analyze the bias of the particle model with a frozen trajectory. So here we are. So of course, in the particle model with the frozen trajectory, there is one over n which is fixed, and the other one which are being computed using the system with the frozen trajectory. So you have two parts. One is the frozen one, and this is the other particles, the other trajectories without this one. So as I said, it's the same as the particle model where you modify a little bit the potential and you add a very small extra jump rate. So in fact, the bias of this is the bias of the Feynman-Cag measure where the potential is this and the exploration is this. So it's almost the Feynman-Cag measure with these two objects is the same more or less as the Feynman-Cag model without this and without this, because you go n tends to infinity. So it's a kind of perturbation argument. So thanks to this, we can prove that you approximate the Feynman-Cag measure with the frozen trajectory here with these two quantities. You have the bias. We know that the bias is T by N. T is because we work on path space. But the Feynman-Cag measure is defined with these two objects. So because by a perturbation argument, we can show that this Feynman-Cag measure defined with this potential and this exploration is almost the same, but you pay, because you perturb all the trajectories, you pay T by N. So if this is equal to this plus this, and this is the true plus this, then of course, this, starting from the Dirac, is the true measure plus T by N. And if you subtract, if you start with the trajectory or start with another, this is the same quantity. Again, you have T by N. And then if you iterate the transition K, T is the length of the trajectory. You iterate this transition N times, you will obtain always Q plus a constant, this factor, power N. So it means that after N iterations, if you have chosen enough particles, at least bigger than the time horizon, so that this factor is strictly less than 1, this tends to 0. So it means that the Markov chain, so the Gibbs sampler, converge to the Feynman-Cag measure exponentially fast. This C doesn't depend on the time. So the question is, of course, what is this C? Or it can be computed, but in continuous time, we have not done it.
Yeah, may I ask a question if you go back one slide? When you say K at the bottom line, K to the power N, that doesn't mean convolve the semigroup of K.
No, this means that the contraction coefficient of T is because we work on the path space of length T.
Yeah.
Okay, so T has nothing to do with the iteration of the algorithm. It's simply the length of the path space, because I'm considering trajectories of length T. So this means that the contraction coefficient of KT is less than this.
But in the equation at the bottom, should it not be Q NT?
No. This is the invariant measure.
This is the environment, okay.
The Gibbs sampler, the Gibbs sampler is here. This is the invariant. If you do one given 2 and 2 given 1, the invariant measure is this one.
Mm-hmm.
By definition of the Gibbs sampler, if you have a measure on product space, sampling 2 given first and first given 2, give you as an invariant measure the law of 1 and 2.
Mm-hmm.
So Q, because I'm working only with X, and I know that it's some bias, I know it's some bias. So if I look at the marginal on X, it's unbiased. So the invariant measure has to be Q.
Okay, so I think my mistake is I'm just putting little n into time, and I shouldn't at all.
Yes, exactly. T is the length of the trajectory. This is the invariant measure.
It's simply an iteration. It's not a.
But in fact, what is interesting to look at is that when you sample according to this Gibbs transition, inside the Gibbs transition, you have Q. The invariant measure is already inside. It's difficult to imagine, but when you computing the transition, is computing the bias of this guy with a frozen line. Computing the bias of this guy with a frozen line is complicated. So we have estimate of that form. And this is the Feynman-Cag model with a frozen line. So again, the frozen line is not so important because when n tends to infinity, these two guys disappear. So you end up with Q. So inside this expectation, so it is this, you have the true measure plus a perturbation. So it's quite rare to have a transition which is the invariant measure plus epsilon. Because it means that with a little probability, you are choosing this invariant measure. It's like if I'm saying I'm sampling, if it's head, I sample with the invariant measure. If it's tail, I do something else. Then the invariant measure is inside the K, the transition. And because it's inside the transition, when you subtract, you see that the contraction is of that order. And then if you iterate n times, you obtain what you want.
Okay, thanks.
So we try to understand better what is the C here. And in discrete time, we have obtained a Taylor expansion like that say that the transition of the Gibbs sampler is the true invariant measure plus the Taylor expansion of order T by N. All of these guys are operators that doesn't depend on the number of samples. So that's a representation of the transition in terms of the invariant measure and in terms of operators that doesn't depend on the number of samples, except the last one. And this says something that inside the transition, we have the invariant measure. I cannot see it in another way, but maybe there is another way of looking at this transition. But the key point is that the transition encapsulates the invariant measure, and these are the Taylor expansions with non-depending operator on N. And we can control all of them independently of the time. So these guys, if you look at the norms, the norms doesn't depend on the time, on the size of the path. The size of the path is here. Okay, that's strange, but this is in discrete time. I don't know how to do in continuous time, but in discrete time, it tells you that if you want to compute the LP norm, for example, of iterate of K, it's the error will be T by N power N, that's always. And here you will have the exact norm of the N iterate of the first order. So I can compute the constant I'm looking for in terms of the iterate of an integral operator, which I know it is described with the coalescent and colored trees, which is way too complicated to understand what's going on. But that was at least our try to understand what is this little c that is arising here. In continuous time, I don't have the answer. In discrete time, I know how to decompose as a Taylor expansion, but not in continuous time. So that's an open question, how to do that in continuous time, or to better explain the constant. I think there is one way to do is to look at the Taylor or bias expansion we did with Rubenthaler and Patras some years ago, and maybe using some backward analysis. I don't know, that's open questions. Yeah, maybe some link which is here is, as written here, yes, you have the unbiased property. It means that what is the law of X is the empirical measure. So this is the mean of the empirical measure applied to F times this. The mean of the empirical measure is not equal to the limiting law, but if I multiply the empirical measure by this, it's equal. But if I put a square, this is not true. So the bias is only on the first moment, weighted by this factor. So we try to do to take the Taylor expansions or things like that, and this is maybe one possibility to look at this type of estimates on this one, to better understand what is here. At least it doesn't depend on time. So I think I'm sorry, maybe I was too long.
Finished? No,
Yeah, I'm finished.
Okay. It is difficult on this environment. Okay, so do we have any questions or comments? Oh, quick, hide your emails. I think I set the tone. I have to ask the first question. I mean, essentially what we're saying here is that, I mean, this is one of the things that I'm quite keen to try and marry up what is done among nuclear physicists, nuclear engineers, and clearly there is a community here who are very concerned with Monte Carlo simulation of Feynman-Catch type objects. I mean, fundamentally, it's the same problem, I think.
I think this Etherington in '84, he really introduced that in physics. In fact, it's a way to compute product of positive matrices.
Right.
Which is the same. If you have a positive matrices, you normalize and then you denormalize. So you create a Markov process and some weight. And when you iterate the matrix, it's the same as writing the mean of a product of functions.
Yeah.
So he Etherington create this algorithm I'm just talking about today. He designed this algorithm in '84 to compute product of positive matrices.
So another question I want to ask is that there is a paper on twisted particle filters, Whiteley and Lee, who might actually be here. Is this a variant of what you're saying with this fixed?
In fact, as soon as you have an exploration and a selection, you know that this is consistent with the Feynman-Catch model with the exploration and selection. You see what I mean? If you give me a genetic algorithm, mutation, selection, and you tell me, okay, I'm exploring the space as a Markov chain, and I'm selecting the guy with a potential function.
Yeah.
Then it's not my fault when the number of samples tend to infinity, you converge to a Feynman-Catch model. You have no choice. Of course, if you write the Feynman-Catch model with X and potential, you can change X into Y and V into W. It may represent the same object. So I'm not saying that the twisted, because there are so many names at the end of the day, you don't know which one is which one.
Yeah.
But the very simple trick is to identify the exploration, the way it explores, and the potential of selection.
Yeah.
See, as soon as you have this, for example, forget about this, just plug a function here. So you explore like X, you select with G, and you will end up, you're obliged to end up with the Feynman-Catch model.
Yeah.
And then you can check if this Feynman-Catch model coincides with the one you had in the beginning.
Exactly, yes.
That's a way to identify things.
So entirely non-unique, but which is what the best one in terms of convergence, right? I mean,
in fact, there are some tries in filtering that say, look, you can, if you have a Markov transition and some potential function, one way is to say, I multiply the Markov transition by the potential and normalize, and I do locally the best thing I can do with the weight. But if you do this, the problem is that locally you optimize, of course, the sample, but it doesn't mean that the variance is improved globally. It's problem depending, I would say.
Okay. Alex, you have your hand up. Sorry, I've been dominating a bit.
Well, I think perhaps I just wanted to first of all check that I understand the last result you had up, this sort of estimate on the
very last.
I think so. So yeah, this estimate you have here. Am I right? So what you're saying here is if I have my n particle Feynman-Catch approximation and I'm trying to sample from the law of the process for the Feynman-Catch representation, and I do it with this n particle approximation.
You are talking about not the Gibbs sampler. You are talking about this maybe. Because the Gibbs sampler, it's a second level. Here, the very first level, if you give me a Feynman-Catch model with a Markov chain and a potential, it's defined by Q. I approximate using the algorithm I have described without frozen things here. I explore like X. If I kill, I jump uniformly.
Yeah.
Okay, this is a very simple way. So this gives me plenty of particles. I take the empirical measure of the ancestral line and I approximate a Q as usual with Monte Carlo approximations. Because you have the CLT, you can do plenty of things. It's not a perfect sample because if you look at the law of the one ancestral line, the law of one sample is never equal to the truth.
Yeah.
It will be equal to the truth plus or minus an error of order T by N. If you work on path space. If you don't work on path space, you just look at, for example, the intensity of the branching process. The intensity of the branching process only look at the terminal states.
Yeah.
Okay, if you normalize properly, this particle model will estimate the normalized intensity measure uniformly in time. If the process X is sufficiently stable.
Yeah.
So if X is not stable, as I said here, you can change. If you have an unstable process, you can change the law so that to make this one more stable. And of course, now you will have another potential function. But you expect that if you have succeeded to stabilize the process, then this will not be so bad viewed by the stable process. Okay, so it's like something we did with Emma on the harmonic oscillator. In this case, you can estimate everything. You can even compute everything. And in this case, even if you have a linear Gaussian model, which is transient, here you have a quadratic term that kills the particle which go too fast. Even if the process X is transient, explosive, the quadratic killing stabilizes everything. So you can say that's very strange. Why? In fact, if you compute the H process, so you change the law of the process, you end up with something which is stable. Because you subtract a drift enough to stabilize everything. So if you have a quadratic potential function and a linear Gaussian process, if you have observability and controllability, in fact, then it's the H process will stabilize any unstable linear diffusion. Because the H process plays the role of a control it's like if you want to control an unstable process, in the control law, you subtract enough so that you control all the unstable eigenvalues of the instabilities. So you have A unstable, you subtract some let's say, matrix in such a way that A minus P is stable. So that's a way to regulate an unstable process to force them to come down. And in fact, the H process do the job for the linear Gaussian model. So I expect it should do the job even for nonlinear and so on. So the use of H processes should stabilize the effect of X in such a way that, of course, if you take the H process, this guy disappears. But if you take something close to it, you expect to stabilize and not to lose too much on the potential.
Okay.
But again, it's a change of you play with one or the other.
Okay, let me just check the chat. There's nothing in the chat. Are there any more hands? Alex, that's an old hand, right? I guess.
It's time for lunch, I think.
It is indeed, yeah. Well, for you, it's time to go for a swim, I think, in Bordeaux.
Yeah, yeah.